In this video, I'll be explaining uniformity targets and mask design, which is the core functionality of UniformityPro. I'll first draw your attention to the Targets panel. As I click on it, I'm now, this is highlighted automatically for me. It shows the type of target, and then also some other information. So starting here at the type, I can click here, and I've got a drop-down box with 8 choices, 4 uniformity target types, and 4 plume. I'll discuss plume in a different video, so right now let's focus on the uniformity ones. You can see we're divided into 2 types, radial and surface. Now I've got surface up right now, and that's just showing that I'm modeling or targeting the whole part. In this example, I've got one big part, essentially, over the whole surface of my planet. And everything's just flat, and so this is a way for me to quickly model uniformity across the whole planet. So with that in mind, here's my 2D surface. Now you'll notice up here it says number of targets equals 48, and down here I've got number of X samples and number of Y samples. So this is a fairly dense, if you would, uniformity plot. And I could speed it up or slow it down by changing these numbers. You know, if I made this 5 by 5, now I only have 12 targets, and so that's going to optimize quite a bit quicker than if I do, say, 15 by 15. So this is a better looking plot, but now there's 148 targets up here. So what to use is kind of up to you and how fast your processor is. Right now, let's go back to 9 by 9. I like that just because it puts, since my diameter is 8, that puts a grid point on every inch. So this is the surface. Let me switch over to radial. And so now this is the same information, but I'm only seeing the targets across the radial line. Let me illustrate that one point further. Right here, I've got the width is 2. Let me make that 5 or even 10. It's going to make these really big over here, but what I want you to focus on is this part. This shows me the location on my part of the targets, and the color right now is red. When I go back over to the surface, you can see now here are all the target points. And so each one of these target points corresponds to one of these colored blocks on this color plot. So let me go back to radial and make these not quite so big. And the source, while I'm here, I'll talk about this. This is referring to which source I want to be targeting. If you have multiple target sources on at once, then you can say total, or if you just want to target a specific source, you can do that here. With just a one source setup, it doesn't matter. Now the other option was uniform spacing versus arbitrary spacing. Uniform spacing just does what it says. I set the number of samples and it puts them uniformly across the part. If I choose arbitrary spacing, now I have to move this down. I get this list, and I can control the number of targets, what part number I want it to be on, its R, or radial value, and then the actual value of the target. When doing uniformity, most of the time you'll be wanting to target 1, which across the whole part would be perfect uniformity. So that's what we'll have here, but then you see there's this plus minus. If I wanted a range, you know, anything within 0.9 to 1.1, so that says that I could be plus or minus 0.1, and that would satisfy. And sure enough, I've got this crossbar here that shows me that new range for this target, and notice that my merit function went to 0 because at these 2 target points, the blue line, which represents the uniformity, is within that stretch there. The delta value allows you to express how important you want a target to be. So lower values, maybe 0.1, would really emphasize this point. and then higher values would make it not as important. Qualifier gives you three options: none, above, or below. So none says that I want it to be within this range. Or if we go back to no plus or minus, I want it to be 1. If I say above, I say as long as it's 1 or above, I'm okay with that. That can satisfy the optimizer. And then, below, 1 or below. So if I make both below, my optimizer merit function will again go to 0 because I've satisfied the requirements here. But again, for most cases, you're just going to want value of your targets to be 1, and then probably no plus or minus 0, but whatever you need. So this is arbitrary spacing. I can change the number of targets and whatnot. Let me go back to uniform spacing, and instead of that grid, I get this Customize Selected Part Targets button. So I'll click on that, and now this opens up a grid where those are now generated automatically. I can't change this R value no matter what I do, but I can change these as I need to. So we'll click OK on that. Now one thing to keep in mind is, I've got 9, right now it's really just targeting the X samples. I've got 9 of them, but it says 8 targets. Well, that's because one of them, the middle one, happens to be the normalization point. And so I've removed that out of the optimizer. It does that automatically. If I put this off a little bit, say 0.5 is my normalization point, see, now I have 9 targets again. And you can see that right at 0.5, that's where the blue line crosses 1. But I'll put it back to 0 for now. So in summary, with the number of targets, it's just a good idea to keep your eye on that, because that'll be have a direct correspondence with how fast the optimizations are happening. You want it to be high enough that you can see what's going on and make sure that you're going to get a good mask shape, but not so high, especially initially, that it's going to slow you down too much. So to start us off, I've started with 3 masks. Optimization is really an art. One of its challenges is getting stuck into a local minimum and not finding a global solution. So for this reason, I'll frequently hop back and forth between various optimizers, and I'll also start with different mask starting points. And that's what I've done here. Basically, I've created 3 masks at different starting points. So let's look at them. First, I've got a full-length leaf, and I just gave it a name to help identify what it is, and different colors so I can keep track of it. So this is maybe a starting point where I can have a leaf that covers the whole part. Another one just kind of starts off somewhere in the middle. And then a third option that I like to use sometimes is this, just starting out with a flat table, or spline in this case, and let it just kind of see what happens. With these 3 starting points, I'll get 3 totally different solutions, but hopefully I'll gain some insights and ultimately find a solution that's good enough for what I need it to be. So let's start out with the first one. I'll bring this up here now, and to select which components I want to fit, I click this Enable Fitting button. And actually see how this box is red right here? That means that I'm editing components of the mask that that's not turned on. So see how this is selected right now, but that box is unchecked. So this is a little visual reminder that I'm actually not doing anything. But if I go up here, there, now this box isn't red. So watch out for that red box. That's there to help you. So let's vary row and the length and the width of my mask. Now let's choose an optimizer. When I come down to the Optimizer and Variable Settings panel, right here at the top is Optimizer. So an optimizer is just different algorithms for performing optimization. We've got curve fit, robo, random, quad, and damp least squares. Quad and random do not use gradient algorithms, while the other 3 do use gradient algorithms. So they just give you different methods to perform optimization. The parameters for all of the optimizers are constrained to the specified bounds, which I'll talk about in a second. All of them have a step size, which is a really important thing for you to be adjusting when trying to find more optimal solutions. So let's start out with damp least squares for now. Here's this derivative increment. You want it to be basically as big as it can be that still works, and then work down to a smaller value. That's kind of a strategy that I have, and I'm sure that there's other strategies out there as well. So what this is referring to is that each variable is given an incremental change in order to find a numerical derivative for the optimizer. The incremental change is equal to the incremental value times the value of the variable at that iteration. So these bounds now are definite bounds, but really the first change it'll say, well, 1 times 0.01. So let's make this let's make it 0.1. And so this will check row at 1.1 and 0.9 first. And notice the color of the bounds. What this is saying is the closer to orange and then ultimately red it gets, shows which way it's leaning. So between 0 and 15, 1 is pretty close to this bound. If I go to 7.5, you'll see they both go white. And then as I go to 14.9, see this is a really dark orange over on this side. If I hit 15, it goes red, so that shows me that I'm on a bound. So as it's optimizing, you can watch these colors just to check what's going on. So let's start it back where it was. I think it was at 1. And let's hit optimize and see what happens. We're starting with 2.75. Wow, look at that. I got down to 0.062825. That's great. Let's expand the scale a little bit. So I right-clicked on this plot and we'll say plot settings. The vertical axis, let's make it 0.99 to 1.01. Now we can see at a better scale what's going on, because this is really good uniformity. So from this point we can say, well, is this good enough? Maybe, maybe not. And so we can change the derivative increment and try it again. We can try a different optimizer. Let's try quad. Now quad uses the bounds differently. It's not a derivative increment, it's a variable increment. And now each variable is given an incremental change in order to fit a quadratic, and then find the minimum of that quadratic. So this incremental change is equal to the incremental value times the difference of the bounds. So here bounds is really important. So with quad, we like to have tighter bounds usually. So if I right-click here on this variable panel, I can fill all the bounds and I have some options. So let's say, well, let's find plus or minus 25%. And so that updated my bounds here. And let's do a 0.01 variable increment. And let's optimize that. Okay, so that didn't get any better. So now you have to kind of ask yourself some questions. Well, do I try a different optimizer, different variable increments? Or do I try to change my mask type? Right now, for example, I've got a symmetric leaf. What if we make this same type, and I'll copy these values, paste them down here. So now I'm starting off the same way, but now I have the freedom to let the top and bottom be a little different. So let's keep our quad, but I'll update the bounds here to be 25% again. And let me hit optimize, see what happens. Okay, we got a little bit better, especially towards the beginning there, but not a big change. So then, well, what other modifications can I make? Next, I can convert it to a table or a spline. And let's say 5 points. So from here, now I've got a 5-point spline on the top and the bottom, and I could vary these. Let me right-click and say Vary All on both sides. What I'm not doing is, when I click Vary All, it doesn't include the first point, because normally we just want that to be 0, but you could manually click it if you want to. So let's move this up now. And now here are all of my variables with bounds. Let me just check the bounds, say they look okay. Well, let me go back and maybe make them plus or minus 50%. And let me try increasing the variable increment just in case it was too low. And let's try that, see if we can get better from 0.2. Okay, it looks like it stopped improving, so I'm going to click stop. Okay, so that made some changes, and you can see that the colors on the bounds are different, whereas they started all white before. One thing I forgot to notice and then mention was that when I converted it from the leaf to the spline, it actually didn't do it quite perfectly with just 5 points, and so that's why that merit function jumped up to 0.2. But with some refinement here, we brought it down. And so again, from this point on, do you want to add more points? Do you want to vary the length? You know, the possibilities are really endless. You could keep going on this as long as you need to. But let's stop here for now, and let's try a different starting point. And let's use quad for now. And I don't know, let's try it with these bounds and see what happens. Okay, not a whole lot, and I wanted to vary that too. Let's switch over to curve fit. We'll try that one now. Okay, so there's a different solution. One thing you can do, in addition to trying different optimizers, is just to change a value and kind of get it to reset a little bit. So maybe I'll try this, setting this row to 3. And it's totally different, but let me just re-optimize from here and see what happens. The merit function obviously went really poor, so it should get better from that real quick. Okay, look at that. Not only did the optimizer get better from 7% where it was, but it's way better than where I had left it, where it got stagnated. So you can see just kind of putting in a value to jog it into a different valley is a very helpful tool. And if you don't like it, you can always go up to Edit, Undo if you find that you didn't like that solution, and that will take you back to where you started. So you can always get back to where you were, but sometimes it's just really nice just to help it along and get it out of a valley. So there's that solution, which you can see is different than the pink one we had, though they're pretty similar, but give us different results. So let's try this one. Sometimes rather than starting with the leaf, I'll just start with a flat spline and let it kind of generate its own shape, and oftentimes you'll see it go to 0 in some points and make high peaks. So we'll just kind of see what happens. So again, I'll enable fitting, and I won't do the row or the length because I want to just let each of these node points vary in place. So I'll right click and vary all. This time I do want to include the first one and the last one. And instead of having an upper bound of 10, let's make it just 2. So if I enter in 2 here, I can click this, this gray square, and if I double click it, it'll fill the column, just like in Excel. Just so you know, I can also select a pattern, and it'll continue the pattern. But we'll keep it at 2 for now. So that's a really nice trick to be able to use to fill a column like that. But let's go to quad to start out with. Quad is nice because it just goes one variable at a time in order here, and it'll even tell you down here which one it's working on. And let's make it, I don't know, 0.05, and let's hit optimize and see what it does. Okay, so what can we see here? We've hit some lower bounds, but I believe that it just doesn't want to be that, especially since we saw in those other leaves that it started about there. So let me turn those off. We'll keep them at 0. Now on this end, this one is a 0, and so maybe it wants to come off there, so we'll lock that one dead there. Now why is this one doing this? Well, we can see here, I'm looking at the part of x equals 4, y equals 0, and see how this line of sight, this point isn't even influence at all, or has no influence on the uniformity. So the optimizer could change this and think that it's doing something, but it's really not. So really, let's just make this 0 and turn it off. Now you saw a small change because it's a spline and not a table. A spline has effect on the other node points, or on the curve. So we did see some small change there, but nothing too big. But here we've hit an upper bound. So let's make this upper bound a little bit bigger and see how high it wants to get. We'll try this again. Okay, so we saw some improvement with that. And if I wanted to, I could probably click Optimize and let it do another 10 iterations. So what I've got is 3 different, but in some ways similar mask shapes. And they all have a different efficiency value because they're all a different size. Let's talk about efficiency for a minute. With this mask, my efficiency is 90%. It's not that big of a mask. This first one, which I think was the biggest one, our efficiency is down to 83%. It's quite a bit bigger and blocking more of the deposit. So if you needed target efficiency, you like this mask shape, you think it's giving you good uniformity, but you would like some more efficiency out of it, you can target efficiency up here. And here we can put some constraints on it. Now here's a moment where you can say, well, I would like it just higher than 90. And now that changes the merit function. Notice if I turn this off, our merit function is back to 0.06. But this is contributing a lot to that poor merit function, so that's going to, if I clicked Optimize, it would significantly change the shape of the mask, but help target greater efficiency. Now, what if that's too strong? Well, remember, I can make this maybe 100. And, well, now that's not going to have very much effect at all, maybe 10. So this is going to have a little effect on it, and it'll try to bring it down. But if I want it really strong, if all I want is 90% efficiency, I can say 0.1 or 0.01. Let me click Optimize. Let's just see what happens. Yeah, pretty quick. I got really good efficiency, but I've lost my my good uniformity. But you can see that there's going to be a trade-off there that you'll have to play with this delta value. Now, last thing I want to say, let's go back and edit, undo, and go back a couple steps to where I was. And then let me go back to this, what we started out with, this is a spline, which is a concept that I've learned over time, that sometimes it's best to start out with a part that's bigger than what you actually intend. Because a lot of times we see that the fringe or the edges don't get as good uniformity. Now this is a slightly more extreme example, but what if I go from 8 down to just 4? You can see, well, my uniformity is going to get pretty good because I'm just going to be looking at these 5 points. So let's go diameter 4 with 5 x samples. And here are those same 5 points. And, well, yeah, my optimizer, my merit function is just 0.0349. So this mask would work great for that. So we got that by designing bigger than we needed, so then it was easier to just make it smaller, and sometimes that's just another tool that's helpful. Like I said earlier, optimization is an art. It's all about starting from lots of different starting points and just constantly playing and nudging and trying to get it to get a better solution until you find the one you need. Okay, let's go back to an 8-inch part and 9 examples, and let's go to this first one that we got a good result with, and we'll turn off targeting efficiency. So once you get a good radial fit, again, if I didn't mention it before, the purpose of the radial was just to get a good starting point really quickly, because we only have 8 targets. When I switch this over to surface, so I'm looking across the whole, in this case planetary essentially, I've got 48 targets now, and that'll take longer to refine, and my scales are a little wide, so everything looks white. Let me change my plot settings. Here I should notice that when you use blue, white, red, I kind of like to have one always be right in the middle with white, and then I can see what's a little thicker than one, what's a little thinner than one. So I just have to keep them the same delta from one. So here we can see, you know, that optimizer, I think with the radial was like 0.06, now it's 0.23. So more refinement can be done here, but at least we've got a good starting shape. You could click optimize and now let it refine more across the surface. So again, these are just more options for you to try out. And that's about it for today. I hope you enjoyed watching this video, and really hope that you've gained some insights on how to have successful optimization.